Hello, everyone. Thank you for joining our webinar, Does This Seem Off? GCMS Techniques for Off-Flavor, Off-Odor, and Flavor Scalping Analysis. The webinar will be hosted by Dr. Jamie Willems of Eurofins SF Analytical. I'm Genevieve Randall, and I'll be moderating this webinar. Before we begin, I'll let you know more about how this webinar will run. The webinar is being recorded, and the slides and recording will be available for you within 3 business days. You'll get an email that has a link to both. A short Q&A session will follow the presentation, and we'll answer all viewer-submitted questions. During the webinar, you can submit questions you have using the webinar sidebar menu. Select the Questions tab, type in your question, then hit Enter on your keyboard. Remember, you can submit questions throughout the webinar. Now I'll give an overview of Eurofins. Eurofins is driven by our mission to contribute to global health by offering the highest quality testing, training, auditing, and consulting services. We strive to listen to our customers and not simply meet, but exceed their expectations. Our footprint is global, with 45,000 staff in over 800 laboratories across 47 countries and a portfolio of over 200,000 analytical methods. Eurofins provides a unique range of analytical testing services to the pharmaceutical, food, environmental, and consumer products industries and to governments. Okay, Jamie, you can begin your presentation, and we will see your screen.
Okay, thank you for that introduction. As mentioned, my name is Dr. Jamie Willems, and I work at Eurofins SF Laboratories, located in New Berlin, Wisconsin. And so today I just want to give you a brief presentation on our technique for off-odor and off-flavor analysis in food and related products. So as I'm sure you're all aware, aroma is an important component of consumer appeal. And along with taste, aroma makes up the flavor of a product. And so off-odors and off-flavors can be very off-putting to consumers and can give consumers a negative opinion of a brand or a product. In addition to this, off-odors may also be a sign of bigger potential problems. So some sources of off-odors include chemical or microbial contamination. Excuse me. So for example, with microbial contamination, this could be yeast, mold, bacteria, and so on, that as they grow in the product, they produce byproducts, which can cause off-odors and off-flavors. You can also have chemical contamination. So for example, you could have contamination with cleaning agents, which can cause an off-odor or off-flavor, or you can get cross-contamination between products. For example, if a product was stored in a container or in a large tank, and the tank was not thoroughly cleaned between the products, you can get cross-contamination, leading to off-flavors and odors. As well, another source of off-flavors and odors is related to this, and this is spoilage due to improper handling or storage. So for example, if a product is stored at too high a temperature, this can accelerate storage, or spoilage rather. So this spoilage can be microbial related, as I've mentioned before with microbial contamination, as microbial spoilage can result in the formation of off-odors and off-flavors. As well, you can also have chemical spoilage. So for example, when we talk about lipid oxidation, so products with high amounts of unsaturated fatty acids are particularly prone to this, where over time the fats will oxidize, giving it a rancid or old fat smell. Another source of off-odors and off-flavors is changes or issues in production. So for example, perhaps you've changed the source of one of your ingredients, and now the flavor profile of your product is off due to differences between the original ingredient and the ingredient you're currently using. It can also be a marker of issues in production. So for example, if a sample is overheated, you can get the formation of heat-related products, such as the Maillard reaction, which can change the flavor profile of your sample. Similarly, for example, maybe your product wasn't properly pasteurized, and now you're getting increased amounts of spoilage due to microbial growth. As well, another source of off-odors and off-flavors is issue with packaging. This can be straight-up packaging failures. Maybe your package is damaged and now you're leading to chemical or microbial contamination. However, there are other reasons packaging can lead to off odors and off flavors. One of these is leaching. So this is where components from the packaging migrate into the product. And in this way, what is in the packaging material makes its way into the food or related product, resulting in an off odor or off flavor. And in the reverse, there's an effect known as flavor scalping. And in this case, what happens is flavor components from the product make their way into the packaging material and therefore are no longer associated with the product. And so these aroma compounds are absorbed by the packaging material, which over time can result in a decrease in the intensity of the aroma profile, causing the product to become muted or a more dull, less bright flavor. But it can also result in a shift or a change in the flavor profile, as different compounds are affected in different ways. And so how do we go about detecting what the cause of these issues are? Well, we do this by looking at the aroma profile of a sample. And the aroma profile is made up of the profile of volatile compounds. When I talk about volatile compounds, I'm talking about those with relatively low boiling points. So these compounds naturally make their way into the gas phase or into the air at room or low temperatures. They then can be detected by the human nose and converted into the aroma that we smell. And our nose can be very sensitive. For example, when we're talking about sulfur-containing compounds, those that give the rotten egg-like aroma, our nose can detect down to part per billion levels of some of these compounds. And so in some cases, it doesn't take much in order to cause an off odor or off flavor. And the overall aroma of a sample or a product is made up of a variety of different volatile compounds. So it is rarely the case that it's only one or two compounds that gives the aroma, but rather a wide variety present in different ratios and proportions. In some cases, you can have dozens or even hundreds of different compounds causing the aroma profile. And so by examining these profiles, or sometimes referred to as fingerprints, compounds which may contribute to off odors and potential sources of the issue can be identified. It is important to note that some compounds may be the cause of an off odor in one product, but a natural and desirable part of the aroma of another product. As an example of this, we can talk about acetic acid, so the main component in vinegar. In some products, you do want that vinegar or sharp acid-like flavor and aroma, while in others it would be considered an off or unwanted flavor. Another example of this is when we talk about cheeses. Some cheeses have very strong and distinct aromas associated with them. For example, think of a blue cheese. This aroma is desirable and an important component of their product identity. However, if you associated these compounds, this aroma with other products, think a fruit or a vegetable or a bread, you would consider that an off odor or off flavor, as it would be very pungent and undesirable. Because of this, one of the most definitive methods for identifying an off odor causing compound is by comparing a good or a control sample to the complaint sample, that is the one with the off odor associated with it. So how do we go about determining what the volatile profile of a sample is? So hopefully with this technical background, I want to give you a bit of an idea of how we approach this from a scientific perspective. And we analyze samples for their volatile profiles using a technique known as gas chromatography coupled with mass spectrometry. This is also abbreviated as GCMS for short. And GCMS is a powerful technique and our flagship approach for the analysis of volatile profiles. The way this works is compounds are volatilized and then separated into a gas phase based on their affinity to a stationary phase. And this is known as gas chromatography. And we can change the separation in the profile we observe by changing, for example, the stationary phase that we use and the instrument parameters in order to target this method to specific products. However, once the compounds are separated, we also need a way to detect them. And we do this using mass spectrometry. And mass spectrometry is a very powerful technique for this, as it not only allows us to detect these compounds, but also aids in identification. So the way this works is that the compounds leave the GC and enter the mass spectrometer. Here they are broken down into smaller pieces, which we refer to as fragments. And the way these compounds fragment is characteristic for that particular structure. And so by searching these characteristic fragmentation patterns against the library of known compounds, we can get an idea of what specific chemical compounds are present in the volatile profile and what are contributing to the aroma of a product. In conjunction with this, we also use a sample cleanup technique known as solid phase microextraction, also abbreviated as SPME. And SPME is a technique for the selective extraction of volatile components from a sample. This allows for increased selectivity as well as sensitivity. This is particularly beneficial when looking at complex samples such as foods and ingredients, as these products often contain a lot of other components such as carbohydrates, fats, and proteins, which would otherwise interfere with this analysis. And using SPME, we can get around some of these issues. And SPME employs the use of fibers coated with a thin layer of polymer material. This material can act as an extracting phase, which allows for the selective extraction and concentration of volatile compounds. And this is how we can improve our sensitivity. And there are a variety of different SPME fibers that we can use. And we can select coating based on the compound classes of interest. And we select fibers based on discussions with the client, as well as subjective observations of a product to try and determine the most likely sources of an off-odor or off-flavor so that we can target this approach to the product that we are currently examining. And so how this works is that samples are incubated in headspace vials in order to release the volatile compounds into the gas phase. We select temperatures based on the volatility of the compounds of interest, with higher temperatures being used for compounds with lower volatility and vice versa. Once the sample has been incubated, the SPME fiber is exposed to the generated headspace gases and allowed to equilibrate so that the volatile compounds and the compounds of interest have time to absorb to the fiber. Then any of these absorbed compounds are thermally desorbed into the GC inlet and separated and analyzed by GCMS. In addition to SPME, we have another approach we can use for some highly aromatic products. As for these types of products, the concentration effect of SPME may not always be desired. In these cases, we use an aliquot of the unconcentrated headspace gas generated during incubation and use that for our GCMS analysis. So hopefully this gave you a very brief introduction to the science behind our approach. I also want to talk about a number of case studies. These look at complex real-world samples and hopefully give you an idea of not only how this approach works, but what kind of data and what kind of information we can get from it. So the first case study we're looking at actually is in a packaging material, looking at an off-odor in cardboard boxes. So a food manufacturer that was manufacturing chocolates was packaging these chocolates in little cardboard boxes. And they had ordered a batch of these boxes from a manufacturer in China and found that these boxes had a funny odor associated with them. And so obviously they didn't want to put their chocolates in these boxes if they didn't want that odor to migrate to the sample, and they didn't want their first impression with the consumer to be an off or a funny smelling box. And so we analyzed these boxes by GCMS to try and determine the cause of this odor. And we did this not only on the off-odor sample, but compared to a control box also received from the same manufacturer. So here on the slide, I have the volatile profiles of the control sample on the bottom and the suspect sample on the top. So I just want to briefly go over what you're looking at here if you're not used to looking at this kind of data. So in these profiles, each of the peaks represents a different chemical compound, with larger peaks being indicative of the presence of a higher concentration of those compounds. And so it is not only which compounds are present or absent, but the relative amounts of them that impact the aroma of a product. And we call these profiles chromatograms, often when we're talking scientifically. But the important thing to note here is when we look at our suspect sample, when we compare it to the control, we can see the presence of a number of additional peaks early on in this profile, which I've indicated on this slide. These peaks were identified as low molecular weight hydrocarbons, which are indicative of the presence of a petroleum-based product. So as I mentioned, our analysis showed the presence of a petroleum-based solvent, such as mineral spirits or naphtha. And so the client was able to use this data to confront the box manufacturer. And the manufacturer of these boxes did confirm that they had accidentally used naphtha in place of isopropanol to clean the boxes. And so in this way, we could determine the source of the issue, and the client could work to correct this with the box manufacturer. So our second case study is going to be looking at an off-odor and off-flavor in a food product. In this case, commercially produced hamburger buns. So this commercial producer had released a number of batches of hamburger buns, and customers were complaining of a vinegar-like or an acidic off-odor and off-flavor in these hamburger buns. And so we analyzed samples of control and complaint products for their volatile profiles by SPME GCMS. In addition, as acid byproducts can sometimes be indicators of microbial fermentation, we also analyzed these samples for their microbial content. And so when we analyzed these samples by GCMS, we found a number of interesting things. For one, analysis showed that the suspect samples had elevated levels of various organic acid and organic acid byproducts, such as 2,3-butanediol, pentanoic acid, and so on. On the slide, I have a zoomed-in portion of the volatile profile of these samples. So this is just a short snippet of the overall profile to give you a closer view. On the bottom, I have the suspect sample, that's the profile in black, and on the top, I'll have our control in pink. As you can see, I marked a peak with a red arrow. This peak was present in the suspect samples, but not found in the control samples. And it was identified as butanediol. And additional peaks were also observed, as mentioned before. And it is likely the presence of these compounds that was at least contributing to the off-flavor and off-odor observed. However, in addition, we saw something else interesting by this method. So here, once again, I have the profile of the control sample in pink, this time on the bottom, and the suspect sample in black. And what we found in our complaint samples was the absence or a very low level of a peak, which was present in our control samples, which I indicated once again with an arrow. And this compound was identified as sorbic acid, a common antimicrobial. However, interestingly, our microbial analysis did not show elevated levels of microbial growth in the suspect samples. So this suggested that the off-odor and off-flavor was a product of production, rather than due to product age or degradation or microbial spoilage. And so this gave the processors a place to start looking in order to determine what occurred during processing to cause this off-odor and off-flavor. In our third case study, I want to talk about a different food product, these little chocolate animal crackers. And so a company was producing these animal crackers, and they were starting to receive complaints from customers that they had an off taste and off odor associated with some of them. And so we analyzed samples of the off odor containing chocolate animal crackers, along with controls from previous batches that did not have any complaints associated with them. And so on this slide, I have the profile of one of the complaint samples. As you can see, there are a wide variety of peaks present here. Most of these correspond to compounds which are a natural and desirable part of the aroma of this product. However, we were able to identify a compound which was present in the complaint samples and not in the control. And I've marked that peak with a red arrow. And this compound was identified as 1,2-methoxy, 1-methylethoxy-2-propanol. However, for this discussion, its exact chemical name and structure isn't overly important. What is important to know about this compound is that it's a key ingredient in a cleaner that was used on the baking line. So what was happening was, between batches, the baking line was being cleaned, but not thoroughly rinsed before the next batch was started. Then those new animal crackers were picking up some of this cleaner, giving it the off odor and off flavor. And so by changing the in-between batch rinse to include more rinsing and greater quality control, this issue could be avoided in the future. In a related case study, we also looked at an off odor and off flavor in a fruit juice. In this case, the fruit juice had an off flavor and was caught prior to being shipped to customers. And so we analyzed these juices with the off flavor alongside control samples. And so what we found is that chromatograms of the suspect samples showed significant contamination with a variety of compounds. And I've marked one of them with an arrow on this chromatogram, or in this profile. And this was identified as 1,2-butoxyethoxy ethanol. And it was identified, as with the chocolate animal crackers, its exact structure isn't super important. But what it is important to know is that it is found in some common industrial cleaning agents. So as with the chocolate animal crackers, this indicated that the products were being contaminated with cleaning agents. And so by improving the rinsing procedure, this issue could be avoided. So now I want to move on to a case study that's slightly different. In this case, a client was observing not only an off flavor, but an off color in one of their products. In this case, we were talking about a pre-packaged alcohol-based food product. These were these little like Jello shots in plastic containers. And so we did comparative analysis on the control and suspect samples. As well, we also looked at the packaging that these samples were in. And so as you can see on this slide, when we compare the control and the suspect sample, there's a rather large and distinct peak in the suspect sample that's not in the control. And this was identified as caprolactam. So caprolactam is an alcohol-soluble component of the ink that was being used on the outside surface of the lids. And so what was happening is, as these containers were being filled, a bit of the alcohol-based product was splashing onto the lids, causing the ink to run. These lids were being stacked and placed onto the product, causing the ink to transfer from the top of the lid to the bottom of the lid and then into the product itself. And so this is where that off odor, or that off flavor rather, was coming from, as well as the unusual color being observed. And so this could be avoided by changing the filling procedure to avoid splashing, changing how the packaging was stacked and stored, as well as looking for a less alcohol-soluble ink. I also want to talk about another issue that can arise from packaging when we talk about flavor and aroma, and that's flavor scalping. So I briefly mentioned flavor scalping in the introduction, but just as a reminder, flavor scalping is a phenomenon where the packaging of a product absorbs flavor compounds from the product over time. And this can have two major effects. For one, we can have a reduced aroma intensity. So the flavor can become muted or less bright compared to the original product. This is because these compounds, the aroma compounds, are being absorbed by the packaging and are no longer associated with the product. As well, we can also see a change in the aroma profile, as not every compound will be affected in the same way. And so some compounds will be absorbed while others will not. And so over time, the profile and the aroma can shift and change. This is of a concern, for example, with plastic containers, but also has been reported in, for example, wines, where some of these compounds are being absorbed by the corks used in the bottles. And so by packaging a product in an incompatible packaging material, you can see a change or a reduction in the aroma intensity over time. And so we can analyze for this using our SPME GCMS technique. And here's just an example of this. So on the slide, I have the profile of a spice-related sample. As you can see, this sample has a wide variety of different peaks associated with it that all contribute to the overall aroma. And so I've overlaid two profiles here, one in red and one in black, representing an initial and a final. As you can see, one way flavor scalping can occur is we can see a decrease in some of these peaks, indicating a decrease in concentration. And therefore, this is where you get the reduced aroma intensity. However, you may notice that not all peaks are affected the same way. That is, not all compounds are affected the same way. And so over time, we can also get a shift in what compounds predominate the profile, changing the overall aroma that is detected and observed. So finally, I just want to talk about one last case study on coffee, a very popular beverage here in the US. And so, as you may know, coffee has a very strong and distinct odor aroma associated with it. And so produces a very interesting profile. And so we received a sample of roasted coffee that had an off-odor associated with it. And so we did comparative analysis between the off-odor sample and a control sample by our GCMS method. And so on this slide, I have the profile of the control sample in black on the bottom. As you can see, as coffee has this very strong and distinct aroma, there's a wide variety of different compounds contributing to this final aroma. So each of the peaks in these chromatograms indicates a different volatile compound, with larger peaks being indicative of those present in higher amounts. And so we can get quite a complex profile off a product such as this. However, we were able to identify the source of this off flavor and off aroma. So in the complaint sample on top, there is a peak which I've indicated with an arrow. And this peak was identified in the complaint sample, but was not observed in the control samples. And this compound was identified as a surfactant or wetting agent that is used in a variety of products, such as pesticides, lubricants, coatings, paints, adhesives, and so on. And so its presence in the product was indicative of contamination of this product, most likely with a pesticide, but it could have been with, for example, an adhesive or a coating. And so this gave the processors a place to start looking where this contamination could have arose from. As well, it indicated to them that this sample was contaminated with products that weren't safe for human consumption, and so they did not release this product. And so hopefully some of these case studies give you an idea of how we can apply this approach to food, ingredients, and related products. And so just to summarize and conclude, SPME GCMS is a powerful technique for off-odor analysis. And by comparison of the profile of a control and suspect sample, compounds that could be responsible for an off-odor can be identified. This can allow for the identification and correction of a potential underlying issue. So thank you all for listening, and we'll be fielding questions at this time.
Thank you, Jamie. So we'll move into the short Q&A. Feel free to continue to submit your questions during the session. Any questions that we don't get to, we'll follow up with after the webinar. Okay, so our first question is, what are typical limits of detection for GCMS?
So with GCMS, limits of detection can vary depending upon what compounds you're specifically looking at and what the sample matrix is. But with some compounds, we can see down to 1 part per billion. But more commonly, we're looking at 50 to about 50 ppb, or parts per billion, to about 5 ppm is more common.
Okay, thanks. Next question is, what other analytical techniques can be combined with GCMS for investigating off-odor and off-flavor investigations?
Flavor and aroma, or flavor is a combination of taste and aroma, and they're closely related. So some other techniques we have used in these investigations include inductively coupled plasma analysis, so we can look for the presence of metals, which might give more of a bitter or a sour off flavor, but they aren't volatile, so we can't see them by GCMS. We also have a sensory analysis by trained sensory panelists, which we can use in conjunction with GCMS to determine the source of an off-odor or off-flavor.
Okay, perfect. Our next question is, when microbiological contamination is determined to be the cause of off-flavor or odor, is it possible to identify the specific microorganism?
Yes, it is. We have collaborate with a microbial group that does microbial analysis. So we have available to us an array of different microbial tests, microbial screenings. We can do techniques such as PCR and DNA techniques for microbiological analysis for identification of what specific microorganisms are present.
Okay. It looks like we've got some more questions. Right. Are there specific techniques that you utilize using SPME to transfer the components from the sample matrix into the headspace?
So I guess the big, one big impact, or there's kind of two big factors when we talk about SPME. One is the fiber coating. So it's important to choose a coating that is compatible with the compounds of interest. So certain coatings target certain classes of compounds. The other important component is incubation temperature and incubation time. So by controlling that, we can help control which and how much of these compounds are transferred to the fiber.
All right, this kind of leads into our next question, I think, which is, what are some of the most common SPME fibers that you would use?
So we have a variety of different ones available. The most common one is a carbo wax. I don't have all the parameters with me, but it's a general fiber that looks at more low molecular weight compounds, which are more likely to be the volatile compounds. But we can look into, but we have more different available that can look at, for example, more polar compounds or gases, depending on what we're specifically targeting.
All right, another question. With complex profiles like coffee, how do you pick out the important differences between samples?
So one of the best ways to do this, as I mentioned, is by comparison to a control sample. Ideally, one that's very similar to the complaint sample. And so the way we do this is we always run all our samples in duplicate, so we can know if a difference is instrumental, so just slight changes in how the instrument's behaving, or if it's due to the sample itself. And then we can compare, looking very closely at these profiles in order to look for differences. What also aids in this is our identification with Mass Spec, which can give us some idea of what these compounds are, as well as targeting our approach by, for example, adjusting what stationary phase we're using in order to aid in separation of these compounds to give us a much cleaner view of what we're looking at.
All right, another question we've received. Do you prefer using a polar column or non-polar column for aroma analysis?
So it really depends on what you're looking at. Typically, we lean slightly more non-polar, but you can get them across the spectrum. You can get very polar, you can get very non-polar, and you can get something in the middle.
Okay, I think this is going to be one of our last questions before we have to wrap up today. What if there are no control samples? Do you have any ideas of what to do then?
So there's a couple different approaches we can take to this. One is to try and identify a sample or a compound that we can use as a reference. So for example, if we're looking at a cardboard box, can we find a similar box? Another is to use commercially available standards for compounds that we know might lead to these off-odors. So if the aroma reminds us of hexanol, we'll use hexanol standards. And if, for instance, you're concerned that perhaps this off-odor is due to a contamination, if you have access to what you think the contaminant might be, we can also run that in conjunction and look at its profile. So if you think your contamination might be coming from a cleaner or a lubricant, we can also analyze the cleaner or lubricant to determine its profile and compare that to the sample to see if there's any signs of indication or any signs of contamination. And we have our database. Like I said, when we analyze by mass spec, we can compare to our database. It has over 300,000 compounds characterized in it. And so we can identify what these compounds are and use that along with scientific literature in order to determine the most likely off-odor causing compounds.
All right, thank you. And the last question we'll ask today are, where did it go? Are GCMS and SPME fairly new methods of determining off flavors and odors? And how long has this detection method been around for?
So GCMS has been around for quite a while now, probably 20 plus years. SPME, I believe, slightly newer, but they're both very widely used in scientific literature, at least. And so they're well characterized for a variety of different compounds.
All right. Well, thank you, everyone, for submitting your questions. Remember, if your question was not answered during this Q&A session, someone will reach out to you afterwards to get you that answer. I want to remind everyone that a recording of the webinar, along with a copy of the slides, will be available to you within 3 business days. You'll receive this via email. Thank you, Dr. Jamie Willems, for sharing your presentation and your expertise. And thank you, everyone, for attending.